The next talk is about inferring typing rules for contextual sugars. And the talk is given by Tailai. You? Yeah. Yes.
So, bonjour everybody. I am Tailai Yu from Peking University, China, and the topic of my talk is inferring typing rules for contextual sugars. So, talking about sugars, I mean syntactic sugars. They are language construct derived from other constructs. The textbook example would be the let binding, which desugars. Yes, the term is to desugar it to an application of a lambda abstraction. And here I would use a fancy D to denote desugaring, and from the notation it recurs down the subterm. So if there are more sugars in E1 or E2, they are also desugared. And it is, used everywhere. So sugars enable reuse of existing constructs. For example, in real languages, they use sugars to keep a small core language and provide sugars as a friendly interface in the surface language. So there are a bunch of examples: dual notation, list comprehension, async await. Even in C, like the pointer to member access is considered a sugar. And we can also, some languages also allow users to define custom syntax as macros, and we can broadly think of them as user-defined sugars because they are also things that derive from other constructs. So I said it enables reuse because, for example, you don't need to evaluate the sugar. You only evaluate what it desugars to. But consider what this works in reality. So for example, in type checking. So real languages, they often manually type check the syntactic sugars before desugaring. This is against the reuse I just said. For example, in GHC Wiki, the Haskell compiler, it says they do this, although this complicates the type checker because there is a chance that your desugaring and type checking has a mismatch, but it improves error messages. So what does this mean? If we just want the reuse, we can type check after desugaring, but this is quite problematic because the errors are reporting in the desugar code. Think of macros when you used the macros last time and errors pop up in something you didn't write. You have to study the internals of the sugar. So we say this is an abstraction leakage. So the abstraction boundary of the syntactic sugar as a syntactic abstraction is broken. So either solution has problems. So can we get the best of both? So we can directly type check the sugars, but without the additional effort that we have to manually write their type checking. And Pombrio and Krishnamurthy came up with a solution. So they, from the core language typing rules and the desugaring rule, they can infer the typing rule of a sugar. For example, this is the let example we just showed. And so the relevant core language typing rules are that of abstraction and application. And the inferred typing rule for let is quite decent. What you would expect. So it type checks E1 first, and then with the binding of X, type checks E2. So the key properties of their inferred rules include abstraction and let's say preservation of abstraction, but they use abstraction for short. It means that no desugared code appear in the inferred rule. So everything is what you have written. No lambda or application show up in that rule. And correctness, which means typing with the inferred rule behaves just the same as typing after desugaring. So there is no point of errors. So how do they do this? We can see that every instance of let desugars to a code of this form. So when we type check this, the typing derivation always starts with a typing rule of application followed by a typing rule of abstraction. And then now the premises are on E1 and E2, desugared, and we cannot go any further. But if we collect the open premises and rewrite them in a form of the surface language, so E1 desugared becomes E1 before they are desugared. So there is a one-to-one correspondence between the collected judgments and the inferred rule. And we can see that inferred rule is just an abbreviation of this partial typing derivation, which is general enough to capture all instances of typing derivations of desugared lets. And this is how they do it. And there are also similar works trying to infer not only typing, but also scoping or big or small big step operational semantics from the desugaring rules, quite like how they did before. So, but there is a very large limitation. So it is that the supported form of sugars is quite limited. They only support simple pattern-based sugars, and the desugaring process is totally fixed. So from a let, they always desugar to a lambda applied, and there is no any kind of dynamic thing, and no any kind of calculation. So this actually limits their applicability. So can we go a little step further? Can we make things a little bit less fixed? So how to make things less fixed? Then a sugar must be able to, for example, read some context. They must interact with something, the context it is in. It may have remote interactions with other sugars or constructs. And this is what we try to do. So concretely, we identify two purposes that context may be important to express a larger set of sugars. And we call these context-sensitive sugars contextual sugars, which appear in the title. So first, there can be multiple constructs that cooperate remotely. The running example would be a pipe operator in the hack language and also proposed to JavaScript. It is not a functional programming pipe. It's like, for example, on the first line, the pipe is denoted by a triangle on the right. And if we pipe a string ABC to the right-hand side, which is so the percent sign denotes a hole. So whatever on the left is piped goes into the hole. So it becomes so the first line would mean that we pipe ABC to concatenate itself with itself. And what we get will be like this. We bind a ABC to a fresh variable x, and then it will be every hole will become a reference to the x. And the important thing is that the holes, the percent size, can nest arbitrarily deeply on the right-hand side. For example, within parentheses, within arithmetic operators, it can nest very deep. It doesn't have to be very close to the nearest pipe. So the second line looks like this. So the point is that if we want to write this as sugars, we see that the whole cannot desugar by itself. It doesn't know where the nearest pipe is, doesn't know what variable it binds. So here we introduce a desugaring context, which is the delta here I didn't explain. So desugaring delta for desugaring context, very reasonable. So we use the desugaring context to pass down the nearest variable reference to the x that was bound by the nearest pipe. And so when we desugar a hole, we just take the delta out. When we desugar a pipe, the left-hand side is still desugared regarding the outside delta, but we pass down the x reference down so that the inner holes can read it. And a second reason that context can be important is that the desugared code can be of very complex structure. For example, they can be scattered. This is a famous type-safe printf example. So printf of a format string is desugared into a curried function taking many arguments that it wants to format. And the point is that, for example, the person S, which should take a string, it first takes a string and then contributes to a part of the final string to print out, or actually concatenated, and they are separated. So we can do this with the context-free pattern-based sugars as before. So I won't go into the details of this example, but the idea is that we can use a desugaring context to accumulate the final string. So the person S, we will see it as a sugar, and then it first takes a string, desugars the left part that takes an argument, and appends the string to the accumulator. Okay, so our work is does this. So we introduce this context to contextual sugars, and we provide an algorithm to infer typing rules for a class of them. And the outcome of our inferred rules share similar properties as Pombrio and Krishnamurthy. So it still preserves abstraction. And regarding correctness, we say it's sound. We will see why it's incomplete, but it's actually something desirable. And it's sound with respect to type checking after desugaring. But there's also some twists regarding hygiene. We will briefly talk later. So as an aside, our formulation of context is a bit similar to syntax parameters in schemes in Racket macros, for those who know. And they are also an addition to pattern-based macros that can allow you to introduce contexts. So you can also think of our work as typing syntax parameters. So how do we do it? First, we start just like the original work. These are the pipe and holes desugaring rules. We form partial derivations for both of the right-hand sides. And it starts out well for the pipe, but it cannot do anything at all for the whole because we know nothing about what delta is. It has no known structure. We cannot apply any kind of rule. So we actually want the pipe to help the typing of the whole by passing down something relevant to the delta. So here's the first step. So we can think of this inferring typing rules as a fusion. So we fuse together the desugaring rule and the core language typing rule. When a piece of core code is desugared out, it is type checked, and so we fuse them. And then it will be very natural to have the fused form to have context from both of them. So both gamma and the desugaring context delta will appear in the surface language's typing rule. This is very natural because the language will have remote interactions. So then, with this partial derivation of the pipe, we can try to rewrite the premises and the conclusion in the new form. And mostly it is natural because like E1 is desugared under delta, and in the rewritten form, it will have delta as it's a part of its typing context. And then E2 is desugared under X, so it is X there. And these still have a one-to-one correspondence. But there are two problems with this partial solution. The first is that we still cannot type check the whole because it actually wants the type of the delta, not delta itself. It still doesn't know how to type check it. And also, there is still a leakage of abstraction. So look at these two x's. You did not write these x's. The x on the left is fine because we can do some. Because the type checking of E2 does not rely on the X binding. It is fresh. So with some clever post-processing, we can remove X of tau1. But this X is the X on the right. It is a variable reference to pass down. So you cannot just erase it. So it stays. And moreover, in more complex contextual sugars, you can think of the desugaring rule passing down a long piece of code as a desugaring context, so it stays. This is not what we want. So we said that we want pipe to help whole to desugar, to type check, but we don't need to pass down everything. We just needed to pass down the relevant information, and during type checking, the information would be the type of X or the type of delta. So we changed the form of the surface language typing rule a bit. Instead of passing the desugaring context itself, we pass down its type. We write as delta tall. And then if we try to write the partial derivation for pipe in the new form, the ones that use delta would just naturally become delta tall. But what about the type of x? So here is the title of where the title of the second step comes in. So we call it early typing because usually you would think that it would be type checked when the whole appears. Now we type check it early, so the pipe takes the duty, and we see that the x is also a piece of desugared code, so we don't want them. So we can just do the same thing as for the main template, the whole right-hand side. We can also form a partial derivation for x, and so it's a reference. So it starts with a rule for variables, and luckily we don't get any new premises. But anyway, if it has open premises, we would want to put it inside the final rule for the pipe. So basically, the final rule this partial derivation says that the type of x will be tall1. So we pass down tall1, which is the type of the E1 that is piping inside. So this would mostly be the final infer typing rule for pipe, and we can also, for example, process away the x binding I just said. And for the whole, it would be much easier because it wants the type of delta, and we are passing down the type of delta. So the typing rule of whole would look like this. It just reads delta tall from the context. This is what the nearest pipe passes down. So finally, our inferred rules for pipe and whole would look like this. This will be very much expected. So like everywhere in the code, you get a type of the nearest thing piped down. And as a recap, we have two steps. First, context fusion. And then in context fusion, we introduced the desugaring context as a typing context, part of the typing context of the surface language. And the second step is early typing, which removes the needs of passing down the desugared code in the desugaring context themselves. We type check them early. So we type check, we form partial typing derivations for every template, not just the main template. And this can be a little bit more general. So delta can be not only one piece of code. It can be, for example, a list of terms. Then we would have a list version of them, type version of them. So delta tall would become like a list of their types. So so far so good. So we did so much to preserve abstraction. So what about correctness? There are some technical things about this, so I will go over this briefly. So we did early typing. So there is actually a mismatch in what context to use. We said this x can be type checked under this blue context, which includes the x binding. So why gamma and x of tall1? Why not just gamma? Because this x is written here under the let binding. This has a this is like some kind of local reasoning. So in early typing in our method, the context will be taken at where the x is written. But with type checking after desugaring, which we must be corrected with respect to, the context is taken at the use site. With this gamma, it is still probably fine because you know, the standard typing context just grows with more and more bindings. So there is, I just said, there is a sort of like a hygienic thing here. So we can, we know its meaning just from where it is written, not at where it will finally reside. So if there is a mismatch between the contexts for both sides. So to ensure that things are correct, we probably have to make the type checking after desugaring a bit hygienic to make them match. And at first, it appears just like a normal hygiene problem. We just rename things, but things get complicated because we want to be general over the core language's typing context. They may be not just bindings. And it will appear, for example, we want to build more contextual sugars upon the language extended with pipes and holes. And now we know that that language with pipe and holes has two typing contexts, a gamma and a delta tau. And the delta tau thing, it simply just can't be renamed. There are no identifiers in it. So here's a example. I won't go over the details, but these sugars build upon the language with pipes. So it desugars to like a pipe and a hole, and early typing would link the pipe with the hole always. But the programmer can also write pipes and holes. For example, they can write code with the yellow pipe and the yellow hole. And then if we just desugar it, we can see that the yellow pipe and the yellow hole intercepts the link between the red pipe and the red hole, which come from desugaring. So this is different from what we would expect from early typing, and there is nothing to rename. So our solution is a bit technical. So think of this is the piece of code on the last slide, and it's written in a tree form. And we see that delta tau, the context for pipes, it indicates where the nearest pipe is. So for example, see the two green dashed arrows. Like if you have a hole at the lambda x of int there, it will find the nearest pipe on the red pipe. And if there is a hole on the right, it will find the yellow pipe on in the middle. So we can think that during typing, there is a typing context at each location of the syntax tree. This is what we would think of normal typing. And to imitate how early typing works, we introduce anchors. So each construct may now point to a location in the tree where it wants to take its context. So most of the construct will point to itself, so it's just still normal. But as the red hole is written on the right-hand side of the red pipe, it will point to the location there. And following the green dashed arrow there, it will just magically point to the red pipe. So everything is linked as expected. So this is still actually only a partial solution to the problem of hygiene of general context, but it is enough for us to formulate the correctness criteria for early typing and our inference algorithm. So the overall picture of the correctness looks like this. So programmers don't need to know about anchors whatsoever. They just write normal terms in the surface language. But the normal terms of the surface language desugars to anchored terms of the core language. And then the normal terms of the surface language are type-checked with our inferred rules, which are sound with respect to anchored typing of the core language anchored terms. And anchored typing, it's just like sometimes a construct just have an anchor pointing up, so it takes the gamma over there. It's actually quite a routine. And the point of why this is not complete is actually very simple, because we are a bit strict. We type check the delta, but the delta in the real world, it can be just dropped. The desugared code may just not contain anything related to the delta, so we are simply not complete. But I think it is desirable because we disallow the sugar to just put any ill-type thing in the desugaring context. And then to evaluate the anchor terms, for example, we can probably reduce them to normal terms of the core language. And this can happen if, for example, the core language typing context is just like kind of like a gamma of bindings. So we can use normal hygiene things, just rename them. OK, to sum up, First, we introduced contextual sugars, and they can, for example, do remote linear actions and allow scattered desugarings. And we try to resemble syntax parameters. And we provide an algorithm to infer typing rules for a class of contextual sugars. The steps are context fusion, which introduces desugaring context into the surface language typing context, and early typing to type check things passed down early. And it preserves abstraction. And to formulate correctness, we introduce anchors, which is a technicality. The programmers or the sugar authors don't need to understand them. It's just used to deal with the problem of we call hygiene of general contexts. And we use it to formulate soundness, which is proved. And that is all. That's all. Thank you.
Thank you. We have 5 minutes for Q&A. Any questions? Yes. Okay.
Sorry for launching into a maybe basic question.
Okay.
If you go back to the very early, the pipe modeling.
The pipe.
Yeah. So this one, right? Okay. Yeah. Next one.
Here,
Yeah.
pipe.
Yes. So. It looks like what you're doing is basically an evaluation of like a programming language with lambda abstraction using explicit environments. That's the delta. And could you basically leverage that you already have lambda abstraction in a setting where you want to work with hygienic macros, basically deep binding, and model this not as a let x equals abc in x plus x concatenated with x, but as abc piped into lambda percentage time dot, and then the right hand side, right? So so basically you have this as a higher order abstract syntax. The lambda would be a higher order abstract syntax. And then press the button for type inference for that, because the lambda then hopefully would be processed by type inference by existing methods. So basically leveraging that you already have lambda abstraction and type inference and type checking for that.
Yeah.
Instead of just going through the way of having environments.
Okay, I think it is very reasonable. And even, like for example, without higher order abstract syntax, we can work with like functional piping. Like we want the programmer to explicitly write lambda x dot x plus plus x. This is also fine, but this is just an example to show how contexts may work. And regarding the higher order abstract syntax, I think it's a very, very, very valuable opinion. I did not think about it, and I will try to think about it later. Thank you. I think very good. It's very good. And actually, we can think of this desugaring as like a meta function, and in a sense, it's similar. I just didn't think of higher order abstract syntax. It's a very good suggestion. Thank you.
One question is that also this example is very complicated. Also, do you have for me, it looks like your theory is treating just this kind of things. Do you have any other good example for contextual sugar?
Probably this is quite general. And for example, they can treat things like this. I think this is very well known. Yes, so we basically just add context to pattern-based sugars, so they are still simple, but like very simple meta-level calculation can be supported, but they can probably not very complex. It has to be compositional, as I didn't say, but these are all compositional. So there is a limitation, but just we add contexts.
Okay, thank you very much. Let's thank the speaker again.